these random variables that are called stopping times. And so a stopping time, this is a map that goes from our sample space omega, and then it takes positive values, including infinity. So it's a random variable, it's a measurable function, such that this here is the key property. When you look at the set, the level sets, these sets here, they belong to ft for any t that you want. Right, so stopping time, this is a random variable. It's a random variable tau, such that this property here holds. And by far the most important example is the first passage time that we looked at last time. The first passage times. The first passage times, this will be tau. It's defined to be the first time that say a Brownian motion is bigger than some constant, say L, right, for some threshold L. And so we see on the picture what it will look like. So we have time out here, and then we have the value of the Brownian motion on the y-axis. And if you start the Brownian motion as usual out at 0, then we put in the level L and say that the level L is up here. And then you run the Brownian motion, and this first passage time is the first time, if there is any, for which the Brownian motion crosses the level L. So this is a random variable, because if here will have one path, this will be b t of some omega, and this is going to give me that value of that, the value of that random time where that particular path reaches the level L. But I could have another path. So let me draw another path, and maybe it comes up here. So this is bt, say of omega prime. Well, then here, this is where tau of omega prime is. So this is a prime that's sitting on there. So I get different values depending on what path I'm looking at, right? So different paths give different taus. Of course, when I have this definition here, I need to check that something like this here is true. So let me just, I'm not going to do that, but if you want, you can find it in here. You can find it in here, and let me just show you where you can find it. Show you where you can find it. Right, so here we have the top part here. This is the definition. This is the definition that I just wrote down on the document camera. And then if you go into this example here, first passage times, and then he gives the argument for why this is true. So if you're interested in why this property 821, why does it hold for the first passage times? This is the first time that x gets to be above. Steve here wrote min. I'm not a big fan of this min here, because it can very well happen that that you never get to be above L, right? So let me draw a path where that fails. So if I start out here, and if I just have a Brownian motion path that goes like this, the blue one never gets up above L, right? So these here are nodes, right? So if BT of omega is less than L, so that's the blue path. This is the blue. Tau of that omega. So maybe I should call that BT of double prime there. It's the path of omega double prime. Then this thing here is defined to be plus infinity, right? And the infimum is never attained. So this here is the inf is not attained. There is no t where you're above. So this is the infimum of the empty set, and you assign the value plus infinity in that case. So here you should see Shreve volume 2, section 8.2. So we did an example, the example we did last time. You spent quite some time looking at these first passage times, and one thing we proved last time was example, we were looking at problem 3, I think. Last time we did problem 3, where one thing we proved was that the probability that tau is finite is actually equal to 1. That was one thing we proved. And we also proved that the expectation was plus infinity. And we did this. So we derived the Laplace transform. So this was the expectation of e to the minus lambda tau. We proved that the Laplace transform was exponential of minus square root 2 lambda, for lambda positive. So that's what we did last time. So we proved that there are paths that, like the blue one here, where you never cross. But if you look at the probability of all those paths, these omegas that lead to such paths, you will have 0 probability. With probability 1, every single Brownian motion path is going to reach a level L. I think last time we did it for the level 1, but the choice of that constant is not so important. You can make that work for any level that you want. So last time we had L equal to 1. And we saw these properties, but the particular choice of L is not relevant for the analysis we did last time. Are there any questions about what we did last time? So let me try to do a few more problems. The next one that I had in mind was problem number 4. I think this was mentioned last time, but let me just highlight it. So if we do number 4, if I take this stopping time that we had, I should take tau to be the first time Brownian motion becomes, say, 1. Then by the previous, I know that the probability that tau is finite is equal to 1. So if I look at b tau of omega, right? So this is this random variable. This is defined to be b tau of omega evaluated omega provided that tau of omega is finite, and then you can put 0 here if tau of omega is equal to plus infinity. But you know that the latter one is has probability 0. So what we get here is that b tau is equal to, well, what is the value of the Brownian motion at the first time that it reaches a level 1? Well, we want to get that this is equal to 1, p almost surely, right? So the probability that these two are the same is equal to 1. And so what this problem number 4 is about is to say that, well, on one hand, so this is just a warning. On one hand, Duke gives that the expectation of BT min tau, this is equal to 0. Like, remember Duke's optional sampling. Duke's optional sampling. Duke's optional sampling theorem says take, well, first you need a stopping time. And the second thing you need is a martingale. So here, our martingale is going to be BT. So Duke's optional sampling theorem says you take these two, you mix them to BT min tau. So that's going to be a new stochastic process. This is again a martingale. Just as BT without the stopping part is a martingale. So you can take stopping times and martingales and you can mix them. And so like that 0 here, this is exactly BT when t is equal to 0. That's the initial value. This is B0 min tau. So on one hand, we have this property, but then on the other hand, you have this one. On the other hand, you will have that the expectation of B tau is equal to 1. So you have something here that is seemingly in you have a 1 here and you have a 0 here, right? So watch out for situations like I'll take the limit t goes to infinity of the expectation BT min tau, right? So on one hand, this is equal to 0. But if I swap them, and I'll take the limit in here, this is going to give me 1. So you have a limit outside the expectation. If you just pull the limit inside blindly, then you're going to get something that is not true, because on one hand you have a 0, on the other hand you have just 1. So be careful when you do this. And so instead, so you need to use dominated and monotone convergence. And so let me show you an example. Let me show you an example on when we can try to do this and do it correctly. This was problem number. Problem number 7. Are there questions on this before we do the next one? So this one here, this question number, problem number 4, there was this warning that you cannot just blindly pull the limit inside and outside the expectations, because you're going to be led to a situation like this one, and it just spells trouble because you have a 0 here and you have a 1 over here. Let me try to do an example where we can see how one can use dominated and monotone convergence to avoid making mistakes like this one. So problem number 7. So now we're looking at we adjust the stopping time a little bit. What we do is we're looking at a double-sided threshold. So we'll be looking here at there's a minus a b here. There's an a here. And then the Brownian motion starts here, and we're putting in these 2 thresholds. And then the Brownian motion runs. And what we're going to do is we're going to stop it. We're going to stop it the first time that the Brownian motion exits this band. So this is the first time for which the Brownian motion is either going to be a or minus b. And so we have a and b here positive. So before we just had a one-sided. Now we have double. We have like this band. The Brownian motion runs in between, and we stop it the first time it comes out. Right, so when tau is finite, so when tau of omega is a finite number, so we have exited, we'll have that b tau of that value. This is going to be a number that is either a or minus b. And before we knew that it was going to be equal to L, or it's going to be equal to 1. Now there are 2 possibilities. Either the path can go up, or the path can go down. So the pencil one, let me call that bt of omega. Then this is tau of omega. If I call the blue one for bt of omega prime, then this will be tau of omega prime. And you can see the Brownian path it's either going to go up to a or going to go down to minus b. So the question is, what is the expectation here? And you see before in that exercise we had last time, where we just had a one-sided passage time, we ended up with the expectation of that one-sided passage time being plus infinity. Now we put in more restrictions, so we might get something that's finite. So what is the expectation this time? The there's a hint in the problem, and it says have a look at MT being, what does it say, T minus f of bt for the function f of x, going to be a quadratic function, and it's going to have these roots a and minus b. So it'll be x minus a times x plus b. It says have a look at this process. Okay, so what does that mean? Let's apply Ito's lemma and see what m is. There's probably a hint in m being denoted by m. So Ito gives us the dynamics dmt. Well, the first one is easy. This is just going to be a dt. Then we need to compute the dynamics of f applied to bt. So then I need derivatives. Okay, so maybe I'll simplify over here a little bit. This will be x squared, and then it'll be x times b minus a b. Is that right? So x, this is x squared. I'll have x times b. I'll have minus a times x. Yeah, looks good. So we apply Ito's lemma to compute the one we have here. So remember Ito's lemma, it says I have a minus, and put a big bracket here. I'll get f prime of bt dbt plus, and then the credit variation term is 1/2, and then f double prime of bt, and then the credit variation of Brownian motion. This is time. So this one here is time. And f prime, what is that going to be? This is going to be 2. So I'll have here f prime of x. This is 2x plus b minus a. And then I'll have f double prime. So this is going to give me a 2. Okay, so I'll take these derivatives and plug them into this formula we derived using Ito's lemma and see what we get. So we get dt minus, and then the bracket f prime, this was 2bt plus b minus a. That was my f prime, and then dbt plus, and then I'll have 1/2 times f double prime, that was a 2, and then my dt. And now we see the miracle. We have exactly a dt here with a minus sign. We have a plus a dt. All in all, this becomes minus, and I'll just have the martingale part, 2bt plus b minus a dbt. Right, so m, we'll write out what m is. So mt equals the initial value and then the integral. So the integral now, the minus sign, 2bu plus b minus a dbu. That's my m, and it's a martingale because this is a stochastic integral. This is a martingale. So I have mt is equal to a constant plus a martingale, so m itself is a martingale. So m is a martingale. And that was one of the key components that we needed to use. We needed to use Dup's optional sampling. Right? Remember, to use Dup's optional sampling theorem, you need to have a martingale, and you need to have a stopping time. And we have these two ingredients. So we have our stopping time, and now we have a martingale. So we can combine them, and we can use Dup's optional sampling theorem. So Dup's optional sampling gives us that MT stopped is also a martingale. In particular, it will be the case that M0 has the same, M0 is exactly the expectation of MT mental. And then you go back up here and you figure out what is M0. Well, you pull in t equals 0 on the right hand side, you're going to get a 0 here, you're going to get minus f of b0. Minus f of b0. Well, b0 was 0, that's where we always start out. So you're going to get that value. And now we have on the right hand side, this is where we have trouble. Because we want to take a limit now. And that limit at some point has to be put inside. And this is problematic. So we know take limits. Take limits, you're going to get that minus f of 0 is equal to, I'll take the limit as t goes to infinity. And what we really want to do is put this limit inside. This is not so easy. And so what we can do again is we can use the definition of m. Excuse me, so I can use the definition of m. I stop it at tau, so I put t min tau here, I put t min tau here, and then I'll take the expectation outside, and then I'll take the limit. So here I'll have t min tau minus f of bt min tau. So we have two components now, and I want to pull the limit inside, and so this is where we had to be careful. This is where these results like dominated and monotone convergence, this is where those results they need to be used in order to avoid making mistakes. And so here we have two terms, and the way that it's set up is that I'm going to use a monotonicity on one, and I'm going to use the dominated convergence theorem for the other one. Like so, first for the monotone, like we note that this map that maps t into t min tau, and this is monotone. But as t is bigger, I take min, right? So if I take t bigger than t prime, then that's going to imply that t min tau of omega, this is going to be bigger than T prime min tau of omega for any omega. So I have monotonicity. This is monotone in T. So I can use monotonicity on the first term. And then I have the second term. This is where I'm going to use the denominator's result. If I look at if I look at BT min tau, then what I'll know is that this is tau is the first time that I hit these levels. This is the first time that I hit these levels. So I will have then that this is less than A and it is bigger than minus B. So based upon that, I'll have that the absolute value of f of BT min tau, and this is going to be less than, and say, I'll take the maximum value of x between minus B and A, the absolute value of f of x, and this is finite. Right? F is a continuous function. We have a compact interval, closed bounded interval here. This is going to be bounded. And you see the right-hand side is a constant. Tau has the omega dependence is nowhere on the right-hand side, and there's no t dependence on the right-hand side. So I can use dominated here. Oh, sorry, I can use monotone here. This is monotone in T. And this one here, this is bounded. This is bounded by a constant. And this is this constant I created on here. So then I can pull the limit inside. Then I can pull the limit inside. Then I can pull the limit inside and I'll get the result. So I have that f of 0, there was a minus sign, yeah, there's a minus sign. And this is equal to the expectation of tau. Put the limit inside. Tau is finite with probability 1. T goes to infinity. I'm going to get tau minus f of, and the same thing here, it'll be b tau. Okay, so tau is finite with probability 1. So we have here that b tau is either a or minus b. And we look at our function. If I evaluate f at one of these 2 points, I'm going to get a 0 because this is exactly how I created. If b tau is equal to a, then I'll have a minus a. This is a 0. If b tau is equal to minus b, I'll have that the second term is 0. So here we're going to get. We'll take x minus b tau times x plus b tau. This is going to be 0. I shouldn't say x here. Switch the roles now. Oh gosh, this is I messed up the roles here. It's b tau that should be x, right? So this here is, this is wrong. It should be minus an a. And then I should have b plus, right? It's x that I'm replacing with b tau here. So I have my b tau minus a. So if b tau is equal to a, then this term becomes 0. And here I'll have b plus b tau. So if b tau is equal to minus b, then this term is 0 to 0. So when I move over here, what I'm left with is nothing else than the expectation of tau. And this one here is simply because f of b tau Let me write it out again, and this time not make mistakes. This is equal to A minus beta times B plus beta. Right, and this is equal to 0 because beta belongs to minus B and A with probability 1. And so this gives me the expectation, and I can write out now here what is this minus F0. It's minus F0. So I have a 0 here. I have a 0 here. This is equal to A times B. So that's the expectation of tau. Any questions so far? Any questions so far? Alice is asking, can we go over the dominated convergence again? Yes, we can. So let's have a look at the actually the dominated convergence says I'm interested in switching, like say I have x ends, and I want to pull a limit inside. I want to put this limit inside. And this is dominated convergence says that this here is okay if I can find a y which is positive, if there exists a y such that you need a couple of properties. So the first one is that the y has to be integrable. So it's positive, so I don't have to take absolute values, but I have to be integrable. And two, it has to be the case that xn of omega in absolute value is bounded by y of omega for any for all n and for all omega. In our case, so in our application, in number, what number was it going to do? 7. Y is a constant. And some people then called, some folks call this version of dominated convergence for bounded. So that's the word, bounded convergence. Because you have a constant. Right, so what was it we had? We were looking at B T min tau. Okay, so now T is our n variable. These ones here are random variables. Right, so I need to find something such that this here is bounded by y of omega. the t variable has to be gone because it's the t variable I'm taking the limit of. So this has to be true for any t and any omega. I have to find such a thing. So that was one property. And the other one is I have to make sure that y is integrable. So when I integrate over my omegas, I'm going to get something that's finite. If I can do that, I can interchange for the limited side. Okay, so let's have a look. See, how big is this one? Well, you know that tau is the first time. It's the first time BT gets out of the band. Right, so T min tau, this is going to be less than T. Sorry, this is going to be less than tau. But we will also have, so this is going to imply that BT min tau, this is going to take its values between minus B and A. Right, because this is the first time I would get to be at the endpoints. So at prior times, I must be somewhere in here. But then you have the then the y you can use will be the biggest one of these two coefficients, right, in absolute value. What we had was then we have to put a function on top of it. Right, so I'll have here that the absolute value of BT min tau, that thing is going to be bounded by the maximum of A and B. And if you want, you can then put a function. We have this quadratic function outside. If I wanted to have this thing, then an absolute value, how big can that get? Well, I'll just maximize over the possible values that f of x can take, because I know inside here I'm between minus b and a. So I'll just let x wander in that interval. Right, and this here is bounded, right? And this thing here is going to be my y. This is my y, and it's a constant. It's not dependent on omega. So in particular, if I take the expectation of a constant, I'm going to be finite. Do you follow that, Alice? Yep. Other questions or comments? I had one more I wanted to do before we start doing American options, and the next one I wanted to do is a little bit more involved, but it's kind of an interesting thing on its own. And believe it or not, I have actually seen applications of this thing. That's why I put it there. So we will not see these applications in this class, but there are applications out there of this result. In particular, there's a PhD thesis by Steve Shreve and a student of his that used this property here. So let me show you. I would say this here is a more advanced application of stopping times than it's one of the more advanced applications of stopping time. So let me try to show it to you. So this is number 5. I take so I look at the geometric bounding motion. I look at a geometric bounding motion. So let me call it MT. So this is an exponential of, say, sigma. We've seen that this is like that's the stock price under the risk neutral measure in Black-Scholes. And then what I do is I define the running max. So I put a star up here. This is just a running max. So this is the maximum over however long we've been running it of mu. I mean, just note here that m0, this is 1, because when I started out, b is 0 and t is of course 0, exponential of 0, this is a 1. So this is my running max, that's the m star. So if I look at a picture, so I have my geometric bounding motion, it will be moving around like this. And so if I look at the max, this here is this is mt of a point omega. I'm looking at the running max, it'll start out here, it'll go up a little bit, then it'll stay flat, and then it will go up, and then it will stay flat, and then it will go up, and it will stay flat, and then it will go up, and then it will stay flat. So the red one, this is my m star t of omega. So here's a crazy question. So here's the problem is, question, what is the distribution of this quantity? So what is the distribution of this random variable? 1 over, and then the limit of this m star. You can see here m star is monotone, so this is just a node. M star t is non-decreasing, right? So it has a limit. So this m star at infinity, this exists. And since it starts out at 1, right, that's the one we had up here. It starts out at 1. This limit here exists in the interval 1 to infinity. Right, so this random quantity here, this is something that belongs to 0 to 1. So I took a geometric bounding motion. So that's the pencil path. I looked at its running max. So that's the red one. And I asked, what is the distribution of this, what is the distribution of this terminal value of the running max? And I call it U. And again, this should probably be an indication that it's uniform. So we claim that the probability that U is less than U is simply just equal to U for any U, well, in that interval 0 to 1. So how would one go about proving this? And you can see here, the question is formulated this way, and there's no mentioning at all about stopping times. There's no, so to prove this, we'll use stopping times. So to prove the claim, we'll use stopping times. But you're not mentioned. You're not mentioned anywhere in the problem. So if you get an interview question of this sort, it can easily be that the solution is going to involve stopping times in this case, even though there's no mentioning whatsoever about stopping times in this problem. Right? This question here could have been asked in the very beginning of a class like 485, after we did something with geometric bounding motion. And the only way I know how to do this is using stopping times. Okay, so let's try to have a look at how one would go about using stopping times. So there are some ingredients we have talked about. So also from last time. Also from last time. From last time, we know if I look at MT and I look at the limit, I would get the 0. So I know that, so there's no star here. It's just that the geometric bounding motion is going to converge to 0 as t goes to infinity, right? So recall that argument, right? This was the one where you said we would write something like e to the sigma bt minus 1/2 sigma squared t. You would write this out. This is my m. This is my mt. I would write this out. I'll pull out the factor t. So I'll have e to the sigma, and then I'll do bt divided by t. And then if I want this to be true, I would have to have I'll have to have a sigma divided by t out here. And I'll have minus 1/2, and I'll have a sigma t here. And I'll, sigma times t here. Get it all done, right? So I think this was right. I factored out a factor of sigma t. And what we did here was, what we did last time was to study bt over t, and we showed that this one here would converge to 0. And the way to think about it is like bt, this has the distribution 0 and then a variance t. And then if I divide by t, then this would have the distribution 0, and then the variance would be 1/t. That was what we exploited last time, because you're going to get a t squared here, and you have a t, and so the t wins downstairs. So if that goes to 0, then everything inside the parentheses would converge to minus 1/2 sigma. And then everything, when you then include the exponential of sigma t, right, then you will get that this converges to, that's going to go to infinity, right? And then you're going to get that this thing would go to 0, because you're going to have exponential of minus infinity, right? And that's your 0. So we did it in more detail last time by computing the probabilities. So here is, I'm just recalling like a little heuristic argument what we did last time. So what it shows here is that mt dies off as t goes to infinity. Okay, so what we're going to be doing now is we're going to try to figure out what this distribution up here is. And the way that we'll do it is using stopping times. Okay, so for a value u between 0 and 1, I want to look at the stopping time. We call it 1/u. This is going to be the first time that the martingale mt becomes 1/u. Remember again that the martingale m starts out at 1. So 1/u, this is a big number, because u is between 0 and 1, so this is a big number. So you're going to have 1/u is somewhere up here on the picture, and 1/u could be somewhere around here. And then what? Well, then then we will have, if I'm looking at the set, where u is less than u, I mean, that's the probability we are hunting, then what would that be? This would be the set where u was 1 over m infinity star. So this would be, I'll just move around, I'll have that this is 1 over u, that this is less than m star infinity. So if the running max, is going to be bigger than 1 over u, then what can I say about tau 1 over u? Well, if the running max is above 1 over u, then that means that the process m has at some point reached the level 1 over u. So that means that this thing here is finite. So these two are the same, right? So if I'm saying here that the maximum process is bigger than 1 over u, then that means that m has reached the level 1 over u in finite time. And the only possible problem here is that it could be that the running max has just reached 1 over u at time infinity, but that's not possible because the value of m at infinity, right? This here is my m infinity. This is 0, right? So it's not going to get over 1 over u at infinity. So you have this chain of inequalities. So that set that we're interested in computing the probability of is exactly the probability that the stopping time is finite. So is this finite, or is it plus infinity? What is it? Well, this is, then we go back through the usual machine. We'll now use dupe and so on. So dupe gives us Dupe's optional sampling gives us that if I stop the martingale, I'm going to get the initial value. Okay, so that's 1. This is my initial value. This is going to be the expectation of m. And then I'll have this tau 1 over u min t. So I need to figure out, so then I'll take the limit. Limit of tau going to infinity of the expectation of m tau 1 over u min t. Now what do I get inside here? Well, again, let's try to work out if I pull the limit inside, what would I get? I'm trying to figure out what this what I have in here. So I'll have we're going to note we did this one last time too, that if I take the limit as t goes to infinity of m tau 1 over u min t, I can split this limit here up into 2 parts. We did that one last time as well. So we had this here would be, I can look at it when the stopping time is finite, plus when it's equal to infinity. So here I'll look at it when it's finite, plus, and then I'll look at it when it's equal to infinity. So this will be when it's equal to infinity, I'll get mt in the second term. And so now I'll pass tau inside. The limit is going to go in. Now here tau is finite, so I'm just going to get m tau. And on the second part, I'm going to get m infinity times this indicator. But we know that this is equal to 0. So I'm just left with the first part. And and when I'm finite, then what is m tau? Well, when I'm finite, m tau is just going to be 1 over u. When this thing is finite, I evaluate m at that finite time. I'm just going to get 1 over u. This here will be 1 over u. So can I pull this thing inside? And the answer is yes, because m bounded is positive. It's positive because it's this geometric bounding motion, and it's bounded by 1 over u. So this quantity here is bounded. So here we're going to use dominated convergence. And I'll put this limit inside. I'll get 1 over u times the expectation of this indicator being finite. And this is, of course, the probability. So what I did was I used dominated convergence, and I can use dominated convergence here because, write that in red. I can use dominated convergence here because the absolute value of mt min that tau is just bounded by 1 over u. So I get now an expression for this, the probability of this thing being finite. This is exactly equal to u. And then I'll just go back to calculations. If I know that this thing here is equal to u, then I shouldn't rewrite it out in detail. Like I had these set relations. So I'll have that the probability that u is less than u. This is the probability that tau 1 over u is finite, and this was u. Right, and this is the proof of u being uniform. So the key thing that happened was was this one here. It related the problem at hand to this stopping time. And then because of that, we were able to use these theorems that we talked about, dupes, optional sampling, and so on. And it gave us exactly that because these two sets were the same, and because this one here I can work out what is, I can now say what the probability of the set on the left-hand side is. And you get this uniform property. If you look at the running max of a geometric rounding motion, the limiting value has this relation to uniformity, which is a property that would be very hard to guess, and I don't know how to prove it without using stopping times. Okay, are there questions on these stopping time problems that we've been through? We've been through a few of them. It's this sheet of problems here that I've been taking from there. I forget how many there are, maybe 10 problems, 14, 15 problems. And they all like old exam problems that have been given out over the years. And if you're interested, excuse me, if you're interested, you can pull it from Canvas. I think at this point it's time to move on to American options and see if I can get you guys ready to solve that last homework problem in number 6. Are there any questions or comments before we move on? Otherwise, we're going to move into American options here. This is section 8.3 and 8.4 in Shreve, and I know some of you have seen this material in various forms and shapes before. Some of you probably have not, and so if you've seen it before, then bear with me. We'll get to something new in a little bit. So American options. This is going to lead to a nonlinear. These are nonlinear problems. Right, so there is an optimization component. And for us, this is going to be an optimal stopping problem. An optimal stopping. So there are there are two versions. There are two versions. So one is a finite time horizon. So you have t running between 0 and infinity, but not including infinity. So let's run it up to some capital T. This here is this is section 8.3, and the good news here is that this is section 8.4. Sorry, finite horizon. This is section 8.4. This is also going to be the one that you have in homework 6, and then you have the infinite. This is also called perpetual. This is when t runs between 0 and infinity. And this is section 8.3. This one here has a closed form. And this one here, there's no closed form. So you really need numerics here. This one here is the one we're going to start out with. We're going to start out with this one, and then we're going to make adjustments. After we finish this analysis, we're going to make adjustments to this one and state how we do this one, and then we're going to look at the numerical adjustments that we need to get the code to work. So the the perpetual one, the perpetual American put. The perpetual American put is given by, and Shu calls this V, and he calls it star downstairs, and then is 0. And this object here, this is defined as V star is 0. So the price of a perpetual American put is given by this quantity here. And this quantity is defined by a supremum. So you're taking a supremum over stopping times tau. Then you're computing expectations under the risk neutral measure of the discounted up to time tau. Right, so there's a constant interest rate. And then the put's payoff in case you exercise is given by K minus S tau, positive part. And we're only going to exercise here when tau is finite. But there's no upper bound here. The only difference between the finite horizon case and the infinite horizon case is whether you have an infinity here or you have a capital T here. You have a capital T here, you're going to get the first one. If you have plus infinity, you're going to get the perpetual one. So the price of a perpetual American put is given by this quantity here on the right hand side, this supremum. Right, so it's a put because it has this K minus, but then there's a tau here. And you're allowed to choose whichever tau you want. So we maximize the expectation over here, over tops. So what we're going to be doing now in the next hour or so, half an hour or so, is to solve this. This is an optimal solving problem. We're going to solve it. And the way that we're going to solve it is going to be doing a bunch of guesses and then do verification. Right, so we're in Black-Scholes. In Black-Scholes, so we'll have a money market account with a constant interest rate. We're going to have a stock which has a well, it has the interest rate as the drifts, and then it has constant volatility. And we'll have some initial, that is 0, that's the initial stock price. So when you're doing Black-Scholes, you want to have your wealth to be given by a function of S. So you'll have, I think we call it xt. This is going to be some function of t and this t. And I want to look at dxt. What is going to be df of t as t? And you can see here that if I have risk neutral dynamics, anything traded is going to have R as its interest rate. Right, so this is going to be equal to R xt dt plus something and then Brownian motion. So this is going to be R, and then I'll have ft st dt plus whatever it's going to be here. So that's the structure. How do we figure out? How to get R here? Well, we apply Ito's lemma. So Ito gives that the dynamics of F, it'll be say ft dt, and then it'll be fx, the derivative with respect to the second entry, dst plus 1/2 fxx, and then the credit variation. We've seen this here a bunch of times, so I'm moving over it a little bit quickly. We'll have ft dt, we'll have fx, and then ds. We plug it in up from the assumption that we are in Black-Scholes, so this will be st r dt plus st sigma, and then the risk neutral Brownian motion, and then credit variation will be 1/2 fxx, and then credit variation of s is going to be s squared sigma squared times 1/2, and then Brownian motion's credit variation is dc. Right, and what I want it to be equal to is rf plus some, I want this to be equal to rf dt plus whatever is here, and then the Brownian motion. Right, so I need to make all the drift stuff here equal to R, and that's going to give us the Black-Scholes PE. The Black-Scholes PE will be R if has to be ft plus, and then you'll have fx xr plus 1/2 fxx, and then it'll be x squared sigma squared. of course, at the end you have ftx. This is going to give me this is the Black-Scholes PE for Europeans. You have at the end, you have this k minus x positive. The question is, how am I going to change this up to get a solution? How am I going to change this up to get a solution of the perpetual American put in the same model? So this is a linear. In the beginning, I said you're going to get a non-linear problem. This one here this is a linear. This is a linear. There's linear PD. There's no optimization. Okay, so now, how do I adjust the quantity I have here to case of the perpetual American put? Well, we're going to make some guessing. So adjustments. So we're going to have some guesswork now. Guesswork for the perpetual. Guesswork for the perpetual. We will have so up here we'll have the value function. This is my Bx. Say S0. So we have S0. Okay. If I look at the hockey stick, so this is K minus the stock price. So if I draw the picture here, this is, let me write it in red. This is, let's see for you guys. This is my K. This is my K minus say S0. So what are we thinking? We're thinking, so this is some guesswork. So we're thinking that when S is big, so when S is big, then what? Are we going to continue or are we going to stop? Well, when S is big, if I stop, I'm going to get K minus something big. That's presumably going to be very small. When I take the positive part, right? So here I'm probably not going to stop, and we continue. We don't stop. Whereas when S is small, we stop. So there's some values. This here is my K, and this here is my K. When S0 gets to be very small, then this quantity here is going to be big. And so we're guessing that when ST gets to be small enough, well, then we're gonna stop and create our optimal time to stop. Okay, so we stop. All right, so there's some critical level. There's a critical level, and say that this is L. This is where, so for the finite horizon, in homework 6, L is a function of time. But now we're doing the perpetual one. So there's no time component. So in here, there's an L. So when S is small, so when the stock price drops sufficiently low, there's some level in here where we stop. That's the guesswork. And now, how would that look like? If I look at this, so here I'm varying I'm measuring S, but I could also have time on the x-axis and then the stock up at the y-axis. So let me try to make that picture. So we will have, say this is time. So there'll be some critical level, because it's what we're guessing, and then there's the strike. The strike is above, and inside here you'll have your S0. So your stock price is going to be moving, and what we're conjecturing is that there's this threshold here that when you get down there, this is the optimal time. This is the optimal time to stop. I think Stevie calls this for tau hat, not tau star. So let me follow his notation and put a hat on there. So when the stock price, becomes L, this is my tau hat. That's what we're guessing. That this is the random time that is gonna this is the random time that's gonna attain. This is the random time that's gonna attain the supremum. This supremum here is going to be the same thing as when I evaluate this expectation at tau hat, if I can figure out what to choose for L. So because time is infinity, we're guessing that the value function, so because of the infinite horizon, we consider, say, f of st instead of f of t st. So we had the PDE over here, and there was a time derivative. So when you have infinitely long objects, then time may or may not matter. Right now we're guessing, and we're guessing the time does not matter. So this term here drops out. So then you just have RF is equal to Fx, and then so on. Right, so so we're going to get the PDE. You're going to get the PDE. This was RF, and then it was Fx x times r plus 1/2 xxx x squared sigma squared. This is when we're continuing. This is when x is big. And then when x gets to be low, this is when we exercise. So we're going to get here that f of x is just the k minus x positive part. This is when x is less than L. Right? Presumably this here is just k minus x. So we're interested in a function. Before we were just interested in a solution to the PDE. Okay, so you switch it to an infinite time horizon. That got rid of the time dependency. In your homework, that's not going to be the case. This ft is still going to be there, and we'll talk about that in a minute. We got rid of it. And so when x is big, this is when we don't stop, right? So we continue. When x is small, this is when we stop. And when we stop, we just get the payout, k minus x positive part. Presumably, we're only going to be stopping when you actually get something that is positive. But we assume L here is going to be smaller, k, right? L is somewhere to the left of k. So what is the goal? Well, we're going to find these values. So we need to find f of x, and we need to find this L. And then show that if evaluated as 0, this is exactly this one that we want. Okay, how are we going to do this? the approach we're taking here is a lot of guesswork. And so what we do is we're guessing and guessing and guessing. And then when we're done guessing, we're gonna go back and then verify that indeed we have found the value function. And as a consequence, we also found the optimal stopping time. This tall head here is going to be optimal. But we need a prescription for how to find L. So let's try to see if we can get it to work. Like here, you can see this is different than what we had before. We did the European one, we don't separate out x's being big and small. This is a new feature, and so what we're going to do is first step is to demand that f is continuous across this boundary. So this is we're going to require that f is continuous across, I think it's only one C, isn't it? Across the boundary. So the way we do that is we take k minus x and just plug it into the top part. So we're going to get r k minus x. And then we're asking, what is it going to be equal to on the right-hand side? Well, this is linear in x, right? So if x is dropping out, this one here is just going to give me, the derivative that's a minus. So I'm going to get minus x. This is going to give me minus x. This is going to give me minus x times. Let me try to do this. K minus x to take the derivative. Let's skip the head now. We could skip the head here, so we could try f of x equal to k minus x also for x positive. And so if I plug that in, I'll get r k minus x on the left-hand side. Is this the same as if I take the derivative with respect to x? That's going to give me minus 1 times xr. But this is going to give me the same. This is going to be the requirement that rk is equal to 0. And this is not true. So at the lower part, when x is small, I'm guessing I have this thing. But when x is big, I am guessing that I have something that is very different. It's at least not going to be k minus x. The thing to note here is that r times k, this is positive. That this is positive. So it's not equal to 0, but it is bigger than 0. So we're going to get this. The formulation is using these complementary inequalities. It's going to be that RF, instead of having equality sign, what we're going to demand is that RF is bigger than or equal to fxxr plus 1/2 fxx x squared sigma squared everywhere. And we're going to demand that f of x is bigger than k minus x everywhere. And then we're going to demand that equality holds at least one place. So we're softening up the requirements that instead of having Black-Scholes hold with equality everywhere, we're now going to say that Black-Scholes holds with inequality everywhere. And it's also bigger than this obstacle everywhere. This was the key thing here with this RK. You cannot have it to be 0, but you can have it to be positive. So these are these complementary inequalities, and this is ultimately what you'll have to solve. These are the things. This is what you need to solve. This is ultimately what you must solve in homework 6. Systems of this sort, where you have, instead of having equalities, you'll have inequalities, and there'll be multiple of them, and then equality has to hold at least one of the 2 places for all x. How does one go about? So in this particular case we have here, we can actually solve this in closed form. So if you look at exercise 8.3 in Shreve volume 2, you will see that if I take the ODE here with equality, right? So now I'm back into dividing the domain up into 2 components. So if I solve this ODE here, if I'm interested in RF being fx rx plus 1/2 fxx x squared sigma squared. If I'm interested in this thing, and this is for all x, if I'm interested in solving this thing, I would have f of x of a specific form. It will be a constant a. I'll have an x here. And now comes the coefficients in the model. It's this minus 2r divided by sigma squared plus, and then a bx. For two constants. A and B. And so now we want to see how does this relate to V0? But V0, that was the value. V0. Page 13, right? V0, you can see V0, this is going to be bounded. Like the puts payoff is bounded by K, this is bounded by 1. So V star, this is going to be bounded by K. Okay, so so then you would necessarily get that V is equal to 0. So V star is bounded. So B must be 0. Then, so what we're claiming now is that we have this A to this power. This is what works when X is big. Right? So what we have here is when X is big, you will have AX minus 2R over sigma squared. And when X is small, you will have K minus X. So this is our guess for V0. This is our V. This is our V star of X. Is it equal to what we have on the right-hand side? Well, we still have two unknown parameters. We have A and B. This is where I was jumping ahead before. So to get, still need A and L. So at the point where it's critical, we demand continuity. So I want, what do I want? I want A I want A x minus 2r over sigma squared. I want this to be k minus x when x is equal to L. So this is going to give us one equation, but I have two unknowns. So we have continuity at this point. The next thing we want to have is differentiability. So what I do next is I take derivatives. Take derivatives with respect to x. Take derivative of this thing here with respect to x. So I'm going to get minus 2r over sigma squared times A times x to this power minus 2 over r sigma squared minus 1. This has to be, and then the derivative of the left-hand side is equal to minus 1. So I have continuity and I have differentiability. This thing here has a fancy name. This one here is called high contact. And it's also called the smooth fit principle. You'll see these words when you read the literature. This is the guess. I want the right-hand side. I want this to be smooth in the sense that it's continuous, and also the first derivative matches up. It's continuously differentiable across the boundary. And now I have two equations and two unknowns. I have L and I have K. I can solve. Solve for A and L. You will get the coefficients. L will be, if I copied it right, 2r over 2r plus sigma squared times k. I'll get A. This is k minus L to the power 2r over sigma squared. And then I can insert up here. I can take these two expressions and I can plug them in here. And this is going to give me the guess for what I think the value function ought to be. All in all, this produces so all in all, we have the guess. F of x will be, I need my A. So that's k minus L to the 2r over sigma squared. That was the A, and then I have x minus 2r over sigma squared. This is going to work when x is bigger than L. And then I have k minus x. This is going to work when x is smaller than L. Right, and remember what L was. L was this 2r over 2r plus sigma squared times k. This is the guess of the value function. This is my function f. It satisfies the PDE with equality when x is big. It satisfies that when x is small, I'm just going to get the payoff. It satisfies that it's smooth across this this boundary L, but it fails. So while f is continuous at x equal to L and differentiable, and also differentiable at this point. It fails to be 2 times differentiable. So if we compute, if you're down here, if I take the derivative 2 times with respect to x, I'm going to get a 0. And if I take the derivative up here 2 times with respect to x, I'm not going to get a 0. So it's not 2 times differentiable, and this is a potential problem. This is a potential problem when you apply Ito. So I won't discuss this, but I will give you a reference. If you see exercise 420 in Shreve, volume 2, you'll find the solution to how to overcome this. One thing to note here is note the difference. Note the difference between f double prime not being defined and f prime not being defined. This one, however, this is our case. This one here is something you also sometimes end up in. So here it could, for example, be if I take the absolute value of bt, right? The absolute value function, if I take the absolute value function, this thing is not, if I take the value function to be just the absolute value of x, then the first derivative is not defined at 0. But that's not the case we have here. We are in this situation where the double derivative is not well defined at this particular point L. Everywhere else it's perfectly fine, but at that particular point it's not defined. And the reason that we get saved is when you apply Ito's lemma. Let's flip back to where we did it. Where we applied Ito's lemma is you had this fxx. This is where you needed 2 derivatives, and that came together with dt. So even though fxx in this particular case is not defined everywhere, it's not so bad. It's not terribly bad because you're gonna be integrating ultimately with respect to dt. It would have been much worse had this fx not been defined, because there you're integrating with respect to, say, in this case, Brownian motion. So these two things are not the same. There's a difference. And thankfully, the obstacle we're facing is the easier of the two. Here, Ito's lemma really just works the usual way. One is okay ignoring these few points where there is no double derivative, because we only have 1 point. That's a potential problem. I think this is a good place to take a little break. Then after the break, what I want to do is I want to do a little bit about the verification, just to show you guys, and then we'll talk about the how to change the numerics in your homework to get the last homework problem done. Are there any questions before we take a little break? So here in the end, what we spent time on was trying to come up with a good guess for what the value function ought to be, and we came up with this. So after the break, what we're going to do now is prove that this here indeed is the value function for the perpetual numeric input. Are there any questions? Or If not, we'll take a little break, like 10 minutes until 10:15 or so, and then we'll do the rest. Alrighty, I'll see you in a little bit.